Hello Internet, welcome to another tutorial in the series of digital electronics. We'll study parity generator today and we'll study a parity generator of 4-bit length. Parity generator is a combinational circuit that will accept a string of bits as input, and it will generate a parity bit at the output which will tell us about the number of ones occurring in that stream of bits. For example, if I give an input 0, 1, 1, 1 at the input, the number of ones are odd. So parity bit which is generated at the output will tell us that the number of bits are odd. And if I change this sequence to 0, 0, 1, 1, it will tell us that the number of bits are even. Now, how does this parity bit tells us that the number of ones are odd and even? That is specified, or that is determined by the kind of parity that is being generated. For example, in this tutorial we are studying even parity. For even parity, the bit scheme is such that if even number of ones are occurring in the input bit stream, then the output parity bit generated is a 0. And if odd number of ones are occurring, then a 1 is generated at the output as a parity bit. So for even parity, the schema will be such. Now, to generate a combinational circuit of a parity generator for 4 bits, we'll need to make a truth table where we'll need to determine what shall be the output, that is the parity bit, for a given set of 4-bit number. So we'll populate this truth table. For 0, 0, 0, 0, the number of ones are 0, which happens to be an even thing. So we'll put a 0 here. Now if we look at the next number, which is 0, 0, 0, 1, odd number of ones are occurring at the input. So we'll put a 1 here. Similarly, we put a 1 here because the number of ones is 1. Over here we have 2 ones in the input, so we'll put a 0, then we put a 1, we put a 0, we put a 0, then a 1, and 1 again, and a 0, and a 0, then we have 1, then 0, and then 1, 1, and 0. Depending upon number of ones at the input stream, we have filled up the output column. Once the output column is filled up, we can put these values in the KMap. So putting the values in KMap will give me a combination like this. Alright. Now we do not have any pairs or quadrants happening here in the KMap. So all these ones will produce a unique product term, and moreover, if the ones in the KMap occur in diagonal positions like this, then we can simply write the output expression of such a KMap to be the XOR of all the inputs. This has been discussed previously also while discussing K-maps, because even if you write the expression for these single ones, product terms, they'll reduce down to A XOR B XOR C XOR D. And this will happen if you change the bits at the input for a parity generator. For example, if you have a 3-bit parity generator, you would get a K-map where the ones will take up the place of diagonal entries, and you can simply write the output expression for parity to be equivalent to A XOR B XOR C. And even if you increase it to n-bit parity generator, the expression would not change. The expression would be the XORing of all the inputs. Now, to realize this, we could use a schema like this. We could XOR A and B first and C and D simultaneously, and then we could XOR the outputs of those two gates. We can XOR A, B in the first stage and C, D also in the first stage. Then we could take the outputs of these two XOR gates and XOR them again to get parity. So that is how simple the structure or the logical diagram for parity generator is. The parity generator can be of two types. We have discussed even parity here. In case of odd parity, this logic would reverse. For even number of ones occurring at the input stream, we'll put a 1, and for odd number of ones occurring in the input stream, we'll put a 0. So odd parity would follow an exactly opposite logic. But the reason why I have discussed even parity is that in most of the complex logic designs, such as that of a microprocessor or a microcontroller, the parity which is followed is the even parity. For example, the parity flag in microprocessor 8085 follows the even parity to check the number of ones in the accumulator to give a result in the flag. So I hope this tutorial was of help, and this combinational circuit is as easy as pie. And if you liked the content of the video, give it a thumbs up, and if you have any questions, drop your questions in the comment section below. I'll try to answer them, and I'll see you in the next video. Take care. Bye bye.